Okay guys, a more straightforward section on Chapter 8, moving away from descriptions for a bit in terms of what forces do and how forces make things change, and actually just going to the mathematics of what is changing. So what is the effect of forces? So if we were to talk about something like this, which in our terminology is an explosion, even though energy may be released from this, how much the things move, in this case 2 parts of a nucleus, how they move depends on this concept of momentum and the link with forces. Okay, so this needs to be considered before we can really understand how forces change things around. So most of it is actually about the kind of level that's in GCSE, so it's really mathematically it's not hard, it's just trying to come up with the ideas of making it nice and clear to somebody. So momentum, old language, the idea of inertia. Okay, so it has a symbol, okay, which we'll come on to. But in your data books you will not see it, but you will see this symbol quite a lot. Okay, so lowercase p equals a lowercase m and a lowercase v, mass times velocity. Okay, now very similar, okay, without the half, and it's not v squared, but very similar to kinetic energy. Okay, now this isn't in the data book, but it is as part of another equation, so we'll come back to that. However, we've looked at that already a little bit when we're talking about wave-particle duality. Okay, so I'll keep coming back to this. Data book tends to use P here and there, not capital P. Very careful. So it's nothing to do with pressure, just be a little bit wary. So there we go, lowercase p. Crucially, this is a property, unlike energy, where you need to consider where it's going. If we're looking at why things happen, then we need to know what happens to those things. So, for example, in our picture again, it's not about how fast they're going, it's not about how much energy they've got stored within their motion or kept within their motion. It's actually about how fast is each particle moving and which direction are they going. So if this was 3 particles, they would not go off in a straight line. Okay, you'd need to think about their direction much more. However, even at this level, anything to do with collisions or explosions, why things move and why they stop moving, is all to do with the direction in which they travel. So we need to think about that direction. We need to think positive and negatively. So vectors, back to that, we are going to look at the idea of adding vectors as arrows again, but today we'll just look at the mathematics. Okay, but yeah, very importantly about that direction, thinking about its motion. Okay, units, yeah, it's not a very neat unit, bear with us. Now, crucially, if we do not have any external force, okay, so there's nothing speeding up or slowing things down, then there is a law of linear momentum, and that linear momentum is conserved. More generally, momentum is conserved without an external force. However, we're just going to consider a straight line, like the pictures underneath. So, what is actually summed up? Well, we need to think about it just like we do with conservation of energy, conservation of moments, yeah, so moments being balanced and so on. We need to think in that similar way. So we're talking about the total, excuse me, can't spell total, the total momentum before whatever happens. So I'm going to just put event. So different types of events, mainly 2 types, is going to equal the total momentum after. And that is how you lay out your maths. You need to do that first line together. So what is that event that we're talking about? Well, basically there are two types, as I say. There is a collision and there is an explosion. Explosions are much easier. Collisions are a little bit harder. So, because we're describing motion, so when we're talking about motion, we're really looking at its momentum, okay, which of course links into velocity, as our equation at the top says. It also depends on the mass. Now, crucially, not here, but crucially, the mass can change during an interaction. I don't mean break up, but actually mass is not a constant property in a lot of kind of scenarios. Now the more straightforward ones that we're doing in this section, yeah, lump 1 hits lump 2. You know, that's what's going on. So the scenario is basically, think of it in the same way. We may have negative values at the end, in which case it will give us a different direction to the arrows, but let's just take the idea of arrows going forwards. Sometimes particles will collide and stick together. So if these were stuck together, coalesced is the phrase we use, then they'd of course have the same velocity because they would be one object. So in this example, before the collision, before the crash, depending on what goes on in the crash, we may lose some energy, but we will certainly keep the momentum as long as there's nothing else going on. Okay? So, in this version here, to take that line and put it into an equation form, what you need to do is think about those momentums that we're putting together. And the easiest way to show your thinking to the examiner, mass 1 with its initial velocity 1, so I'm going to use a u, I'll use a v for the final velocity. So that plus the second one is going to equal mass 1 velocity v1 plus mass 2 with a second final velocity v2. Okay, and it's worth putting, if they, and I'll put the word in here just so we can you can recognize the word, if they coalesce, okay, it's coalesce, coalesce. If they coalesce, i.e. stick together, then what will happen is you've got m1 plus m2, which will come out with a single value of v, so you don't need to split it up. Okay, so worth keeping those together. Right, let's look at an example and see what this means, what this tells us, and kind of the bigger picture. Now, if we turn over the page, there we go. I've got an example on the next page to give you a closed system. So here we have something which we call a closed system, which means nothing else is introduced. Okay, so there's no external forces, it's kind of sealed off, it is just this event that's happening. So again, we can use that phrase quite a lot of different places. Now if we put them together, obviously I've not got much room here. I'm going to pick up on little details because I need to introduce these two ideas here. So we're going to look at the momentum in total, and we're going to look at the total energy in its motion. So actually it's all about kinetic energy. Worth putting in the units, of course, so that's in joules, and that, unfortunately there's not much space there, I'm going to squeeze it in kilogram meters per second, okay, just to be a bit awkward. So if we work out the values, I've got 8 times 6, which of course is 42, and sorry, 48, he says, yes, 48, plus negative 9, okay, so that gives us negative 36 kilogram meters per second squared. Okay, so that gives us a whole total of plus 12. Okay, part of that motion is cancelled out by part of that motion. The momentums partially cancel out. What is left over is 12. Okay, if we do that with energy, similar thing, don't forget it's half mv squared. So don't forget to square it, common mistake. We've got 144 plus 162, which is going to equal 306 joules. So that is what we've got with two objects about to collide. What will they do? Well, what I've done here is the longhand version of the answers, whereas you look at different scenarios, see if they can happen, see if they can't. And it depends on both of these factors. It depends on how much oomph it's got, how much motion it has, and also how much energy, because obviously energy is also conserved. So we have two conservation rules, both are really important. So this one's a bit easier. These have coalesced, so just put that in, just so you can, from the previous page, go, that's what it means. So they will deform and they will stick together, so they'll somehow mash together. Again, normal year, I'll do a demonstration with the air track, we'll see if we can get that done. So if we put that in, what we've got is simply 12 times 1, so I have plus 12. It's 12 and it's going rightwards. Okay. When we put the energy in, we find that's only 6 joules. So a little bit more interesting there. What's going on? Well, in terms of, again, I haven't shown you the working because it's just one lump. We'll do it for the others. But that's showing that some of your kinetic energy has gone. Again, don't forget, it's just the motion energy. So it's lost some motion. It hasn't changed its motion. It's moving, it's still got it, but it's lost some of the energy in its motion. Okay? Not its ability to produce a force, that's to do with momentum, which we have here because that hasn't changed, but its ability to actually make things happen. Has it got enough energy for something to happen? Okay, so they're kind of two different ideas. Why it happens, is there enough energy to make it happen? So if we put the next one in, we take that one first. I've got minus 8, 8 times 1, and I'm going to add on the plus 20. So again, that adds up to plus 12. Fine, still same, so momentum is conserved. If we look at it in terms of energy, I've got 4 for kinetic energy there, so half of 8 times by 1 squared, plus on the other side I've got 50, and that's going to equal 54. Okay, so it's managed to keep hold of more of its energy because it's collided and unstuck. That's one of the main things. So if you have a coalescence, if things stick together, it has coalesced, then what you'll find is you will lose an awful lot of the motion, the kinetic energy. You'll use it to deform the objects to make them stick together. And it doesn't matter if it's lumps of car that are sticking together or whether it's nuclei in an atom, nuclear fusion. That's the same process going to happen. Okay, you will lose energy to the forces, the internal forces. Notice I said internal because it's closed system. Okay, so there's no forces happening from the outside. You can't see them in the picture, so don't make them up. Next one, minus 24 and plus 36, so that's going to equal, again, still 12, that's fine. We have, in terms of energy, 36 plus 162, so again, that's still less, but the fact that these, the one that seems to be having the most effect is actually affected, so there's a bit of a ratios thing going on, it means that more energy kind of gets kept. But just simply going off, yes, it can make it happen, yes, it's got enough energy, so they must tie together. And if we put them on to the next one, again, very quickly, minus 32 plus 44, that adds up to plus 12. Okay, so again, all good. But what you get with these speeds, okay, the faster speeds, what we end up is we end up with those two numbers adding up to 306. Okay, so these three are inelastic collisions. Energy of its motion, its kinetic energy, is not conserved. Obviously energy is conserved, but its kinetic energy is not conserved. So these, if you put it down the side, the first three are inelastic collisions. And do make sure you've got kinetic energy there. So it's not energy itself. This one here, I think we can squeeze it in. That is an elastic collision. Now, if we look at the remaining two, it's a couple of examples, and these cannot exist. So you can't tell by looking at them. The numbers perhaps seem a little bit high there. The masses certainly still add up. We've still got 12. With all of these, we have our 8 and so on. But you know, how much it'll bounce off? 48, 36, momentum. Most of it's going rightwards. You know, here, yeah, that's kind of getting more to the left. So it seems unlikely. This ricochets off faster than it came in, and yet it's the heavier mass. So if you look closely at numbers, you might be able to figure it out. But more importantly, if you do the maths, it's very easy to sort it out. Because if you put that in, what you'll end up with for momentum wise is that can still happen. That looks good. However, when we put the energies together, what you'll get is a rather large value, 594. So that is more than we started with. We have gained energy from somewhere. So if these are hard little particles and there's no other process, that is not possible. Okay, that is impossible. So energy is not conserved. So that's not possible. Excuse me, conserved. Just note, by the way, going up in energy is also non-conservation. It's not about losing energy, so to the surroundings and so on. In the second one, if you do the maths of that one, numbers are a bit lower, and again, speed makes the most difference with energy. But if we put those together, we end up with those two adding up, which still gives us the right value. So 306, 306. So perhaps it is possible. But actually, when you look back at these numbers and you put those in, what you'll get is 64 backwards. That's an awful lot of momentum, plus less so forwards. So it's kind of more obvious than number 5. Number 6 really shows fairly clearly, I think, from the numbers, if you look carefully at the numbers, that this can't happen. The heavy thing would not bounce back unless there was some other force. So again, this one, momentum is not conserved. So both of those bottom two examples, bottom two outcomes, just make that clear, because they all have the same starter, but they all have different possible endings that you're checking out. The bottom two cannot happen. They are impossible because it doesn't add up. The energy or the idea of momentum doesn't add up. Now this does give us a hint leading into our next section, so we'll pick up on that. That minus 44, that direction pushing to the left, does make an interesting addition. So it gives us a hint that there's something else going on if it were to happen. Okay, let's move on to the second part, which is the second type of thing. We treat it in exactly the same kind of way, so we still use adding up the momentum before, adding up the momentum afterwards, but rather like my starting place, what this explosion started with is a single lump. And let's assume that it's not moving. If it is moving, then these two velocities are added on top of the original velocity. Okay, so relative to each other, you can still work out these two velocities, whether this is moving or not. But let's assume then, to make it easier, that this is not moving at the beginning, and then it splits into two different sized objects. And if they have different sizes, then they have different velocities, because their mass affects the velocity. Now the pattern, before we go any further, is worth pointing out at this place. Notice this has a small mass. So what we'll get here is a large velocity, because this is a big mass. So I'll take that into W, excuse me. A big mass so it's going to be a small velocity. So it doesn't matter how you look at it, you can't get away from this fact. Basically, large masses tend to move much more slowly than small masses. Small masses move really quick. They're far more maneuverable. They don't take as much force to make them start moving. So yeah, in terms of its movement, heavy things, massive things, tend to have a lower velocity. But why is that? Well, it's quite easy to prove if we go back and use the basic equation. Okay, so in this scenario, everything is sat still, which means that, I'll put it down the side here, P equals 0. Okay, small p, notice. Here I have a large mass and a small mass. Cannons are going to be a lot more massive than the cannonball. That means that one's going to move off with a lower speed. That small mass moves off with a higher speed. Can we check? Yeah, we can basically come up with what I've just shown you. We just need to think about what it's doing at the beginning, which is simply 0. Okay, so for an explosion, 0 equals what we've got at the end. Okay, in other words, if we want it to add up, then all of this at the end must also equal 0. If we rearrange that to just make that a little bit more convenient, I'm going to put, because it fits with the diagram, I'm going to move the mass 1, velocity 1 across, so momentum of the cannon, I'm going to move over to the left hand side, so I'm going to subtract it, so I subtract it from here, and that's going to equal mass 2, velocity 2. So straight away you can see it's all about the ratios of the mass and the velocity. So bigger mass has a smaller velocity to give you the same value, but also it shows us the direction. So the recoil of the gun moving left, is equal to the momentum of the cannonball going right. Okay, so that's worth pointing out, that idea, and you'll always get that effect. If you throw a ball, you are going to get a bit of a push backwards. Okay, you try standing exactly upright while throwing a ball, you will wobble backwards. Most of us tend to use our feet to balance our load a little bit. Now let me just pick up on crucial a little bit, is all of this, shall we say, straightforward idea, nothing complex about it. It's just, as I say, all about getting that bit of maths right at the beginning. All of this just gives us an idea of how much oomph something's got as they're moving, or how much difficulty it is to make them move. But it's that idea of, yeah, once it's moving, how difficult is it to make that change? But it hasn't told us how we make that change. And obviously, how do we make things change? Forces. So I'm just going to move into a very small section which links perfectly into our last bit. Okay, so we've got things moving. They weren't moving before. Because they're now moving, they have accelerated. But where is the force going on in here? Well, if it was a collision, it's a bit easier to think about, but not always. Not if they're not solid. So for example, if you are struck by a blast of air, it can knock you off your feet, but there's not really a mass that hits you. Okay, so you can't really create a force, not in normal terms. We'll look in further detail next year, but it's quite hard to get your head around. So what we can do is actually go back to Newton's laws, and the second law is the crucial one. And as I said so far, F equals ma is not quite true. It works for some occasions. It works for many occasions, to be fair. So scenarios, if you're thinking about, I have a resultant force, then that's going to make a mass accelerate. So that's an idea of acceleration linking with force. Mathematically, we need a bit more detail. And so what I'm going to do is think of it in a slightly different terms, which is, how does it relate to momentum? So, here we will derive backwards. It's not a proper derivation, so it's not from first principles. We're going to derive backwards from the simple version of the GCSE where we had F equals ma. Well, we know that a is the change in velocity, v minus u, per time. Okay? Or sometimes conveniently called delta v over delta t. Okay, so again, not very helpful, but a nice little shortcut. So how much time it takes to raise our velocity from u to v, notice we haven't covered that in the ideas of collisions. We haven't said how long the contact time is, but we'll come back to that. But if we put those together, then what we're going to get is the force. I'm just going to leave yourself a bit of space because I'm going to add a bit here, notation. But mv minus mu over the time is taken between those two values. Okay, so we can have these as vectors. This idea of a vector quantity, momentum is a vector quantity, I can subtract them to find out change in direction. We'll do a bit next year, but actually, in fact, right at the back end of this year. But usually we're just going to think of it as acceleration, but it's far more powerful, far more flexible, far more usable if we keep thinking in that terms. So, this is the version in the data book. I'll be precise, it is the average resultant force. So I'm going to put in resultant there. So that is the effect of an external force changing the momentum of this mass of stuff, whatever this stuff is. So again, in the data book, this has been shortened to, and we could talk about the average force, so F bar, the mean force, is going to be delta mv over delta t. It's interesting they've put that because, again, they wouldn't allow it with acceleration. So this is actually the more useful equation. But if you can look at your data sheet and pick that up and go, aha, that will give me this. Now, if we want the force at any moment, because it's always changing, then we actually need to be talking about not how much change you get per second, but actually the rate of change at that moment. So as it says there, that's the idea of the external force. Okay, and obviously takes place in direction of the force. So, excuse me, if the force is from behind, the velocity increases. If the force is from the front, the momentum that the moving object's got slows it down. Force changes its motion, Newton's first. How much it changes motion depends completely on the change in momentum. So not change in velocity, but change in momentum, because in real life mass will usually change to some extent as well. Okay, so this is far more powerful. But if you want that instantaneous one, so at any moment in time, then as I put down here, it's actually dmv, or p if you prefer, dt. Okay, so it's that rate of change, but not in the data book. So this one is in the data book. Okay, usually you've got two different speeds. So what I'm carefully saying with that, or rather with that, not using that, is that we're not actually looking at what's changing as it collides. What we're looking at is how much force did it take to move these two particles off with these certain speeds. Okay, and notice we're talking about speed, velocity, not acceleration. So it's a bit more important. It's a bit more user friendly. It's a bit more to do with the graphs, because you're looking at change in velocity per second on a velocity graph. We can interpret it as acceleration, we can call it acceleration, but actually it's all about how that momentum changes. So more profound idea than the last one. Okay, how does it link into things? Well, in real life, this is what's happening during the collisions. It's changing, so overall we'll take that one. But if we are moving at a certain speed and we want to produce as small a force as possible, then we need a really large time. Okay, so for example, climbing ropes are very stretchy, not to absorb energy, although it is an inelastic collision. What happens is it's about increasing the time that the force is exerted for. And if you put those two together, that will give you how much force is needed to change that momentum. So a falling person is a falling person at a certain velocity. The more stretch in the rope, the bigger the collision time, the smaller the force. Stunt folk, when they're jumping off something, they'll jump onto cardboard boxes and giant airbags and things like that, because they crush, and as they crush, they will increase the time in which the force is exerted for. If we want to take it a slightly different way, okay, I got a bit 3D here, let's skip past that. That's all to do with car safety, and it's the idea that basically you are like an egg. So if you were catching a cricket ball, it would hurt because it has a lot of mass, it has a lot of momentum, and it's very hard. So that will hurt if you catch it instantly. But if you let it land in your hand and then let your hand slow it down, then it doesn't hurt so much. Likewise with an egg. If and again, we normally do this in the lab, but if you want to try and catch an egg, then again you move the egg in your hand. So there's more time slowing it down. That requires less force. Brilliant.